data curve, which is really what's actually really been happening to data, and it's just to give a backgrounder, right? And the idea of giving people a reasonable appreciation of the way that in one way or another data has actually exploded, because it's not completely obvious, it's not a straight line thing. So that's the beginning of that. Then there's the fact that the hardware layer, that technology, computer technology at the hardware layer is being incredibly disrupted right now. And because it's being incredibly disrupted, we don't really know where everything's going to go. But the whole point about that part of the presentation is just to give you a feel for how disruptive what's going on at the hardware layer is right now. And then I'm going to talk about analytics, and then I'm going to talk about BI, in the sense that I regard the market as always having been split between people that did analytics with a specific goal in mind, and people that did BI. So I'm kind of, that's kind of the agenda I'm going through. This is about the data curve. This is, it's always been like this. It's like, as far as you can go back to the beginning of IT, and about the 1960s when it really started to roll, data's been growing at about 55% a year, and it's exponential, you know? And there's nothing new about that. And if you actually look, if you go and Google old surveys as to the growth of data in the year 2000, or the growth of data in the year, 2002, 2004, Google only goes so far back because the internet only started so far back. But, if you look at it, it's kind of about 55% every year. It just does that, and it's doing that right now. And there's nothing new about that, But data growth, so, and that would indicate that there isn't any reasonable justification for the word big data. But actually there is, and that's kind of what I wanted to point out. Even though the data's been growing, it's been growing at about the speed of Moore's law. Moore's law leads you to a multiplication of about a factor of 10 every 6 years. So with the increase in computer power, we've had data growing like that, but the databases have grown much faster. And this is a really interesting thing. And the way, I look back, I did this in about 2003, 2004, I kind of looked back at what had happened, because I was doing presentations on what were called VLDBs in the 1990s, and the VLDB was something that was multiple gigabytes, very large database. And I kind of looked at it, and when I started looking at databases, we measured them in megabytes, tens of megabytes maybe, that kind of time, and a really big database was 100 megabytes, and about 5 or 6 years later, which is one order of magnitude of Moore's law, we've gone into gigabytes, and then 6 years later we've gone into terabytes, and 2009-10 we went to petabytes, and we're going to exabytes by 2016. So this is an order of magnitude of 1,000 every 6 years. And this is really odd. And nobody noticed, when I started pointing this out to people, they were going like, really? Are you sure? And then they would look at, the history of it, and really the history of it is that the biggest databases are actually new. It isn't the databases that we built before that are growing. They're probably growing about 55% if they're growing in any serious way, and not all of them will be. But they're probably, if they're growing, they're probably growing at 55%. But the new stuff, the databases that, Yahoo and Google and Facebook, etc., had to build, they were entirely new applications. And they were built, actually, with entirely new technology, because the old technology didn't work. And this is one of the keys to what's happening in the database market. The reason that Oracle is doomed if it doesn't buy one of its competitors that's coming to give it a bad time in the market, is that its technology was built for this. It's built for this time. And the databases that are coming out now, and there's quite a lot of them, it's not just one or two, the databases that are coming out now, they're built for this. And they're built in a completely different way, and the architecture is completely different. So that's one of the things to kind of understand as to what's going down with data. This was a graph that I came up with in about 2004. And I was trying to understand, because I'm an analyst, technology analyst, I'm supposed to in one way or another project going forward what's happening to technology, you know. So I drew this graph and I was trying to encapsulate what was actually happening with the Moore's law increase in computer power. And so what I've got up here is response times. This is a factor of 10 each time. So this is a logarithmic graph. If it wasn't a logarithmic access, if it was just a straight standard access, this would be about 5 miles in the air. You know, so it has to be logarithmic. And I've drawn curves as to what we could do in 1960. And what I'm doing here is that I'm vaguely messing around with the idea that there is different sizes of workload. And that's already a complicated idea because, you know, a workload can have a lot of I/O, in which case it's I/O bound, or it can have a lot of memory bound, or it can be CPU bound. So it's the combination of those three things, actually now you have to add in the network. But it's a combination of those three things that make up what a workload is. So workload size it could be large because of a lot of I/O, and it could be large because of a lot of calculation. And that's what this access is, you know, and you can just see the waves of technology. Every 10 years, where we actually seem to get an increase in speed, somewhere in the region of a factor of 10. And maybe a bit more than that, but you know, you can see these curves coming forward, and then you get this effect, which is the application migration. That, you know, when we started using email, we probably, if we were the early users of email, we were using it on an IBM mainframe. And then later we would be using email on a PC device, and then later we're using email through an email server and a PC, and then we're actually using email through Gmail, you know, which is kind of the popular model right now for actually doing email, you know. But the email hasn't changed. But this has changed. It's the architecture's changed. So we've got migration from one application to another application to another application because they got trapped in their architecture and they got subsumed and replaced. You know, and this happens all the way along. And I was looking at this and trying to get some idea of what's going to happen in the future. You know, and we start to see every 10 years or something, but every 6, 7, 8 years, you start to see a new thing emerge that you couldn't do before, but you now can. So you can look at an area like operating systems, and at various points in time, there are major changes to the operating system, but by the time it had got to about 2001, 2002, there was so much power being delivered that you could actually have virtual operating environments. So VMware suddenly came into existence. It came from nowhere, right? It was like nobody kind of expected that. And I was trying to foresee what might happen, you know. And then we had, you know, the complex event processing market suddenly came from nowhere. And what had actually happened was that things had got fast enough to do stuff we couldn't do before. So I was trying to get some perspective as to what would actually happen in the future. And I drew out this curve, and it lasted for about 6 or 7 years. So it was kind of usable. And now it's bullshit. Right. Because it started about 2012, 2013. I started to run into application. I was looking for order of magnitudes of 10 times faster than before, should change the way an application works. Once you get 10 times faster, you should be able to build it in a different way and maybe deliver something much better than you've done before. But 2012, 2013, I started to run into things that were 100 times faster and 1,000 times faster. And we never had that before. We really didn't have that before. And this is what I'm going to talk about in terms of the great disruption, because there is huge disruption going on in the market because of the things that you can do at the hardware level. There's actually some huge disruptions, things you can do at the software level as well, but you know, this presentation is about the hardware layer mostly. The kind of takeaways from this diagram is that, first of all, you know, software architecture's changed. So we had centralized and client-server, and 3-tier web architecture and service-oriented architecture. And we were able to build in smaller and smaller components, in effect, was what was going on, and to distribute them across multiple execution environments. And the applications tend to migrate according to latencies. If something can get faster, then you may get a better version of any particular applications out there. So the dominant applications and software brands die by what's called the Innovators Dilemma. They make their money out of working in a particular way, and something comes and just sideswipes them because it works in a completely different way. And it wasn't directly competitive, it was indirectly competitive. Gmail didn't come out to compete directly with Microsoft's Exchange. That wasn't what was going on. What was going on was they could just do it that way, so they did it that way, and there's a complete different set of users. It was the the individual consumer that started to use Gmail, and then all of a sudden, all organizations are using it. It's the dominant one. Wholly new applications appear. I already talked about virtual machines and CP, but you can come out with an awful lot of examples of that kind of thing, where all of a sudden it was possible to go a lot faster. You can even, relational database in 1990, when I started to look at it, was just hopelessly slow. And it couldn't do LTP. And they were trying to, in one way or another, justify the fact that it could do LTP. But every time they were ever given any of the relational databases, whether Ingress or Oracle or later Sybase, when they put into a situation where they actually had to do fast transactions, they couldn't do it. Well, 10 years goes by and it's just dominant. The relational database could do it. And it wasn't because they wrote better software, it's because the hardware got faster. So this is about the great disruption. And this is, I don't know where this goes, so that's the reason for kind of introducing it. It's normally, I could sit down and say, I think that the market's going in this direction, I think certain things will happen. But there's so much disruption going on right now that I haven't a clue what's going to really happen beyond, a couple of years' time frame. It's really difficult to predict. First of all, it's over for spinning disk. And it really is over for spinning disk. We talked to Samsung, who are the makers of the flash drives, the solid-state disks. They now reckon that SSD is on the Moore's law curve. Well, solid-state disk is already about 10 times faster than spinning disk. Well, in 6 years' time, it's going to be 100 times faster. It's already price competitive with with spinning disk. So, in 6 years' time, it's over. And IBM, I think, early last year, announced that they're investing $1 billion to completely change their own storage technology to be all solid-state disk. So IBM has completely voted in favour of this. The spinning disk is dead, And the reason it died was that they couldn't get the seek time to improve. It's like, there's two speeds of spinning disk. One is just reading off the track as the thing circles, and the other is moving the head. And if you actually look at the way that disk speeds improved over a period of time, they could read the stuff, they could make it spin faster and read off the disk faster, but they couldn't make the head movement any better. And because of that, you started to get a huge disparity between the speed of memory and the speed of disk if you're doing random reads. And that just started to skew the architecture, so people start to build things differently, Well, all the traditional databases, this is amusing, all the traditional databases are engineered for spinning disk. I mean, I did analysis of these throughout the 90s, and you discover that 50% of the software in a database is actually about pulling data off the disk. It's about caching, it's about doing various things to try and make it really, really likely, better than 95%, that if you want some data, it's in memory already. That's what they were trying to do. Well, when you don't have spinning disk, all that code can be thrown away, and that explains a whole new. And I could probably do a whole presentation for an hour on the new database products, but I'm not going to talk about them at all much. There's the in-memory disruption. When you build an application, the assumption is that the data that is the prime source of data lives on disk, right? And we've done that for decades. Right? Well, we've now got to the stage where that doesn't actually have to be the case anymore, that the prime source of data can actually live in memory. Well, that changes everything as well. And this is another disruption on top of the problem with disk. Right? Almost all applications are not built to organize data in memory. All those databases, they weren't organizing the data in memory, they were organizing caching. So it wasn't a case that those particular products were making excellent use of memory. And there are a whole series of techniques of compression, of vector processing is another one which you can do on chip, of binary chops to get at information when you're actually looking for it. It's completely different to the way that you would index data if you're pulling data off disk. And nobody was building for that. And there's a whole set of products coming out now that are trying to, in one way or another, provide for that, you know? And then, so memory has become an accelerator. Well, the fundamental fact is that memory is 100,000 times faster than pulling something off a random read-off disk. But it's really only about 3,000 times faster if you've got really good caching going. But 3,000 is big, you know. So if you've got a small amount of data, then it's starting to be the case that you probably should be building the software to be in memory all the time. It's very easy to now. It didn't used to be, but it's very easy now to have it completely fault tolerant. You know, to just distribute in one way or another between two places that may even be, you know, hundreds, thousands of miles apart. And if one falls over, the other continues. That's all very, very doable, and it didn't used to be easy. So that's in memory, but this is probably more, really? Oh, I going in the wrong direction. This is the memory cascade. Action did this with VectorWise, and IBM has been doing it with DB2, and there's a company called Sisense in the VI space that's been doing this, and I'm starting to run into this again and again and again, and it's like this. You know, there isn't a lot of L1 cache on a CPU, but it's actually 100 times faster than anything else. If you can process data in L1 cache, it's 100 times faster than L2 cache, right? There's only 32K of it, so you can't really use a lot of it, but there's a quarter of a megabyte of L2 cache, and that's 30 times faster than L3 cache, also on the disk. And there's 8 to 20 megabytes of that, which is like a PC from way back in the 90s, you know, they're all on the chip, you know, and that's nearly 10 times faster than RAM, you know? And RAM is about 300 times faster than SSD, and SSD is about 10 times faster than disk. You know, and you look at that, and it's a memory cascade. And this is like we talked about, in one way, we talked about structured storage in the past in the mainframe, and we were talking about data on tape and data on disk, and data storage in one way or another to try and make the speed at which you get data. Well, this is the same game, except the cascade is right from the CPU chip. And you can do stuff with this that makes a really big difference. One is that if you can get vectors up to the chip, then you can process, in one instruction, you can hit 8 pieces of data all at once, so it's 8 times faster. You know, but there's another thing that you can do, which I think is really a really smart thing, which is that you can keep all your data compressed, so you make all of the data fit into memory, right? And it's all compressed, so it's taking up much, much less space than it would do otherwise. And the only time you need to decompress it is when you process it. And if you can get the compression to that before you decompress, you have a huge performance win. You know, so this is CPU. You know, the actual usage of CPU, and it's only just started. There's another. I mean, I should talk about. It's a company called Velocidator, but there's nothing particularly interesting about them other than that they did this, which is they're taking a whole ETL game, which is, you know, to transfer data from here to here, and transform it and maybe do various manipulations on it. And it took an Intel chip, a GPU chip, and field programmable FPGA, right? And the FPGA is really, really good for serial processing, so you can put logic on it. And you can design your own FPGAs. And then the GPU is absolute for parallelism, so anything that's parallel can go on the GPU. And then the control of flow can go on the Intel x86. So I had 3 different chips, and they put the logic all on this. And they were doing ETL. And it was 1,000 times faster than Informatica. they were actually, it's like the data's coming off one server and going to another server. It's going between this appliance. This appliance is in the middle. But it might as well not be there because it's the lag it puts into it. It's like a tenth of a second. It's nothing. Right. And previously you had a server there that was running sometimes the ETL software, and the lag was hours. And it's like you only need to think as to what a difference it would make to your life if, when you flew from America to Australia, you could fly 1,000 times faster. You would get there in a minute. You wouldn't have time to do anything, actually. You get on the airplane, it'd take an hour to load the airplane, and then a minute later you're in Australia. And you're getting off the airplane, and it's like, was there any point in doing up your seatbelt? It's a bizarre thing to have something go 1,000 times faster. Well, why is this happening? And it's not any specific thing. The reason it's happening is that in 2004, they ran out of the ability to improve the clock speed of chips. And they had never had multiple processing, multiple cores on chips, except in very specialist high-performance computing machines like the Crane machines. They didn't do it. They never did. All commodity chips had one processor on them. In 2004, they couldn't increase the clock speed anymore because it ran the chip too hot. So they had to actually divide up. They could still make the circuits smaller, but they had to, in one way or another, add more processors to the chip so they could claim that the next generation of chips was going faster than the previous one. But now it's going faster because of parallelism. Well, nobody ever wrote software to run parallel. Well, now they are. Right, well, as soon as you actually extend that out beyond the individual server, because you wrote the stuff to run parallel, you can now assemble 20, 30, even 1,000 if you want, servers, all of which with lots and lots of processors, or you can have parallelism coming out of your ears. We never had it before. And that's why we're getting stuff that can be 1,000 times faster. And that's incredibly disruptive. It's beyond any kind of disruption we've ever seen before. It was already too hard for us to anticipate what Moore's law would give us. So loads of companies just go down because they got sideswiped by something that came later. Well, at 1,000 to 1, this is the most disruptive world we've ever seen. And it's not going to stop. And and then there's the SOCs. I'm talking to a couple of companies at the moment, and they're talking about system on a chip. Well, when you have system on a chip, you don't have that cascade anymore. The idea is to put as many system on a chip as you actually need. And by the way, there'll be the ARM chip because it uses less. Probably be the ARM chip because it uses less electricity. And from the chip you can get at the network, and from the chip you can get any storage. But the idea is to have everything happening on the chip, put many of them in parallel, and they'll blow out the water anything that you can do now if you can find some low-hanging fruit to get the system on a chip market going. And there are a number of people that are trying to do this. So this is the disruption of 5 years' time. There are SOCs that can run Linux, for instance, so you could put whatever you wanted on a SOC. And that would just blow away everything that's going on right now. And everything that's going on right now is blowing everything else away anyway. So it's like, I know what's going down, Don't ask me, you find someone smarter than me. So, and this is the revolution, this is the architectures. The original computer, it was all batch processing. When it went online, you had a centralized architecture. With a PC, you had a client-server architecture. The internet, you started to go to multi-tier. With mobile, that's about the time the service orientation happened. And then the Internet of Things is about event-driven. And this is just a huge change. Right? And the thing that, it started a while ago, but it's starting to become more and more obvious. But the idea of Internet of Things is really that every incremental change to anything gets reported. So it started with, they wanted to capture the clicks that any individual did on the internet. And then you got this huge click stream that had to be processed. But, there would be like hundreds of clicks before anyone ever bought anything. So what you previously had was a transaction, and that tended to happen all at once within any application that you'd written. And all of a sudden, we're having this just event-driven situation. Well, as soon as you acknowledge that this is happening, then you actually get into the whole of an organisation's processing should really be thought of in a set of event streams, because that's what you're handling. And there were people maybe 3 or 4 years ago that were building systems like this, and there are now people that are very seriously building systems like this. It's like, we never built like this before. We just didn't. We didn't talk in terms of events, but the sum total of what is happening to any given operation is expressed in the events that are happening to that operation. So if you didn't have any computers, you have a completely greenfield situation and you just started to build stuff now, you would build it for events. You wouldn't build it for transactions, you'd build it for events. You wouldn't use any of the applications we have right now. And this was the set thing, which is you start processing things in event windows, and you can start correlating events and start recognizing various things that you couldn't actually recognize before. So that was a new departure in BI. But what will actually happen is we'll have to have a traffic cop thing. The idea is that everything out there is sending events to the network, and there's a traffic cop that, at the speed at which it arrives, filters, replicates, and routes all of the events. And you have real-time operational intelligence type applications, other applications. You have catching the data either in a data warehouse or in what they're calling a data lake, but I prefer to think of as a data reservoir. And that's what it kind of looked like, but that's very, very crude. And that's enough of that. That's enough revolution. That's do the data science thing. This is the thing that happened with big data was that you could all of a sudden process data that you couldn't previously process before, because various organizations were actually able to bring data in from the outside. And what had happened with analytics before that was it was a kind of walled garden, and it was like the pharmaceuticals companies would have their data analysts, and the banks, the banks had quants, so they'd already compromised the situation. The insurance companies had data analysts. There were various industries, some of retail had data analysts, various industries, but it was all kind of walled garden, which was the data came from within the organization, and then all of a sudden you can get it from anywhere. And the really big disruptor here was the social networks, which suddenly became really interesting to analyze in terms of the data that they actually had. And the reason that it was interesting was, apart from anything else, this was data that had never been gathered before, but data that hadn't even existed before. So you're suddenly getting possibly streams of data coming from outside, and it's not just social network data. There's lots of data that we didn't previously process, and then people started talking about a data scientist, and the question is, what's a data scientist? And she didn't mean to do that. My graphic go. My graphic didn't work. Doesn't really matter. Data science project manager, qualified statistician, domain business expert, experienced data architect, software engineer, right? In other words, it doesn't exist. Those people don't exist. There isn't anybody who could do that. So it's a team, right? So with the advent of big data, they invented this new profession, which immediately had anyone who was a data analyst suddenly declared themselves to be a data scientist. But they actually had required no new skills in order to take this new title. And when you worked out exactly what they had to do all of that. And no individual could do all of that anyway. It's without shadow of a doubt, it was a team. But there is the fact that it's not that easy to understand data. And this is a really good example. What this is a trend line drawn according to a root mean square, which is a good way of drawing a trend line in certain circumstances, right? And these are 4 different scatters of information that will give you exactly the same trend line. And anybody who's ever done data analysis work knows this stuff. But somebody that's just given a piece of software that says create a trend doesn't know. And what's wrong with it, this is actually a genuine trend line through scattered plot points. This has got an outlier, so the trend's wrong. And any normal data analysis person would know that was an outlier. And the same happened here. This is an outlier. And the real trend is up there. I think this is not a linear trend. It's not, you know. And people that have messed with data for many, many years and served the apprentices know this stuff. And people that are just the normal business analysts don't know this stuff. And therefore, to give them really powerful data analysis capability is dangerous. It's expensive as well. But it's also dangerous, you know. I like to look at the world this way because it's a simple thing. Hindsight, oversight. Most of what I think of as BI, which is the normal users are using it, was hindsight and oversight. Look, the hindsight is looking at reports of what's happened in the past. The oversight is looking at what's going on now, so it's dashboard type of thing. So, you know, hindsight would be OLAP, or, you know, it might have sophisticated reporting capabilities. It might be just lists of stuff. It might be good visualization. It doesn't really matter. It's looking at what's happened. And then you've got oversight, which is looking at what's going on now. And then you've got foresight, which is projection of trends into the future, which is now, you know, the day of this and the day of this, right? There's not much new going to happen here. You know, we may get slightly better visualizations and so on and so forth. We may get, because we can bring lots of data together we couldn't bring before, we may report different things. But we're not going to get much new emerging in this space. With foresight, most organizations haven't done much of this. So predictive analytics has got a long one, in my opinion, it's got a long, you know, at least another 5 years where new stuff may happen. But it all actually comes out of exploration of data. It all comes out of insight. And I like to look at, you know, at this as being BI, and I look at this as being analytics. But this is starting to change because there's no reason why you shouldn't give the ordinary individual, as long as they understand what they're doing, there's no reason why you shouldn't give them an exploration capability. And that is what's happening in BI at the moment. Exploration is going out to everybody. But those are 4 separate activities, but there's a 5th one called optimization. And the only thing I'm going to say about this is that mathematically, optimization is not a solved problem. You know, so you could look at any given organization, you can say there's got to be a best way of running this and investing the right amount of money in the right place and making the right hires and putting in the right technology and machinery and so on and so forth to make it run. But it's like, if you can get an answer that works, that's great. But there's no answer that you can claim is best because there's no mathematical proof as to what is best, because it's an unsolved multivariable mathematical problem that will probably never be solved. You know, and it's of the ilk of the salesman's route. You know, the idea that a salesman's got to make 10, 20 calls or something, and you've just got to get the best route between the various, so that you spend less time on the road and more time talking to the customers. That's not a solved problem. You know, and it's been sitting around in mathematics for hundreds of years. It's not a solved problem. So optimization is not a solved problem. That means that there's probably going to be a career for guys like me for at least another 10 years, because it's not going to become a solved problem, so I can bullshit about it. Data analysis is a process, not an activity. So it's a multidisciplinary end-to-end process, right? And it's like data access, data preparation, modeling, analyzing, deploy, execute, audit, continue, round. That's how data analysis used to be done and probably should be done, right? This is, the interesting thing about this is it's very, very difficult to optimize this. It's not, in my opinion, easy to optimize at all. And when you do get an optimization, it's not necessarily the best one, as I said, mathematically not proven. Until recently it's a walled garden, but now data from outside, and the fact that Hadoop allows you to gather data so very, very easily, greater data availability, much more scalable technology, open source tools coming out your ears, it's all become an anarchic space, you know. But there are some kind of important things, really. If you actually look at trying to optimize it, you realize that there's a lot of different latencies to make this work at the speed that you want it to work, if it can work at that speed. So, you know, even though we might have the ability to make things go 100 or even 200-300 times faster, the question is where we're going to put the rocket fuel in order to actually make the end-to-end process go faster, because it's the end-to-end process that matters. You know, there's data access, data preparation, model development, execution of the model, implementation, model audit and update. And those are things that, if the latency goes out too far, starts to make a mess of the analytical activity. Just a fact. And that's where the rubber meets the road, because speed actually does equal value if you get the data, if you get the analytics working, firing really well. This is the impact of machine learning. We didn't do this before. We knew about it mathematically, but we couldn't do it because we didn't have the computer power. And so we believed, at some point in time, we believed that we hired data analysts, and let's say it was in the pharmaceuticals, looking for new drugs kind of area, and they would grab all sorts of data and they'd try and find patterns and correlations between various things, and we would trust them. We would say that because this guy's been messing around with this kind of data for 4 or 5 years, he could look for patterns possibly everywhere, but because he's got a really good gut feel, he's going to make all the best decisions, right? Well, that's wrong. They never were that good. None of them. And they start to discover this when they start to use machine learning algorithms, which is machine learning algorithms give it a lot of power, and you have it investigate every possibility, and they start to find things that most data analysts never found before. And they never found them because they assumed that there was nothing there to find. You know, they made assumptions, but the machine doesn't make any assumptions. It tries everything. But you see, if you start to do, you know, if you have a table, let's say, with 1,000 columns or something like that, and you start to do cross correlations between the columns, you know, it could take months. You know, this is not reading the data off the disk. This is like manipulating the data in memory. It takes months to examine all correlations. But when you can make stuff go 1,000 times faster, it suddenly only takes an hour. You know, and that's the kind of thing that's going down with machine learning. And that's going to be really, really disruptive. And then there's this, you know. You can know more about a business from its data than by any other means, you know. Einstein didn't say that, but I said it. More credibility if I put Einstein's picture. The math is going to beat the people. You know, the math. You say the computer power beat the people, beat the best chess players. I know 10 years ago when IBM did that thing, and then it started to beat the players of Jeopardy, I know, a couple of years ago, and that's created the Watson technology. You know, well, when we actually properly apply data analytics to running an organization, it's going to beat the CEOs and the CFOs. It's going to beat them. And there are a lot of CEOs that I would like to see go down in this way, but you know, it is actually going to beat them. And this is a different organisation, if you can actually, in one way or another. But it's a long way to go before you get there. The thing to say about this really is that data analysis should now be looked at as business R&D, because that's what it is. You know, so I've had guys ask me questions like, how much should the business be spending on analytics? You know, if it's getting results, how much should we be spending? The answer is the same as the answer of how much should an organisation spend on R&D? You know, and if you actually look at different organisations, very successful organisations that spend small amounts on R&D, and very successful organisations spend large amounts of R&D. It's not an easy to answer question. But the thing is that we shouldn't think of analytics anymore in the way that we thought of it before, as a kind of activity that's got, you know, a few guys in a room that have been told by some executive or other what to do. They should be looked at as research and development of the organisation. And that's going to happen because, apart from anything else, the data scientists that don't really exist got so much great publicity that they suddenly got a lot of power. Okay, so that's the analytics world. This is the consumerization of BI. It's like, I did this section really because I ran into too many articles that started to talk about the democratization of data. And I was kind of sitting there, and I went to the dictionary, and I just tried, what's that mean? Does anybody know what democratization of data means? Does it mean that, you know, does it mean that a big database gets more votes than a little database? What does it mean? You know, and journalists were sort of asking about it, and I thought, oh, what it means is actually consumerization. It's not democratization at all. That's bullshit. It's consumerization. So this is about this. Now, what I'm about to say is extremely radical, right? And I also think it's extremely right, you know? We're talking about human beings. human beings work in the following way. We have three fundamental nervous systems. Right? One of them is the enteric nervous system that lives in your gut. Right? And it processes in one way or another the internal operations of you as an individual. Makes your heart beat. It changes your breathing, stuff like that. Stuff that you don't know how to do, but it does. You know. And then we've got another nervous system which is down the backbone, which is the reflex response thing. So you touch a hot stove and you don't sit there thinking, shall I or shall I not remove my finger from the hot stove? You just remove it, you know. Those two systems, they're extremely fast response. So if we take an analogy between an organization, a company, and the human being, or it doesn't even need to be the human being, because actually animals are pretty much like this as well, you know, there's two data flows that have got to be real time. One of them is a response to what's going within the organization, the other is a response to what's happening outside the organization that needs an immediate reaction, because the organization will die if you don't react to it at one point in time. This is I think, the pattern that's going to determine the way that business, that analytics and business intelligence actually pans out, you know? So, almost instant reflex, swift response, and a considered response, and it's like, you know, there are some people like this, but mostly there aren't people like this. That's just, I decide to buy a car, you don't a quarter of a second later know what car you're going to buy. That's like a considered situation, and you may in one way or another do more, you gather a lot of data, talk to people and so on and so forth. It doesn't mean you're going to make a good decision, but it does mean that you're going to actually consider it over a period of time. That's analytics in the way that I've kind of talked about it, a detailed investigation of something. So this suggests two data flows, or possibly three. One which is extremely real-time data flow, the other which is near real-time data flow, and another which actually has to be as fast as, because you want your thinking to happen very fast, but it doesn't actually happen to be real-time at all. It's more in terms of whatever the business urgency of what it is that you're trying to decide is. So that's what I think is actually happening in the in the industry right now. You know, I'm already starting to detect in various organizations that are doing what I would call various advanced stuff, division into two different data flows. You know, and one of them is a real-time data flow. And if you're doing predictive analytics, there's really no point in doing predictive analytics unless it leads to action immediately. There's just no point. You know, there are loads and loads of data analytics projects that were left on the shelf. They're left on the shelf because they'd found something really, really useful and it couldn't be implemented by IT. You know, here's the pattern, but the IT was just too hard, didn't happen. Then there's real time and business time. There's a factor that we think of real time as less than a tenth of a second, but there's a business time. I think the real time is the business time. It's the speed of the operation of the business. So certain businesses like banking need to be extremely fast, and construction is much, much slower, you know, to take two ends of a spectrum. And we should build specific architectures for that. So this is the idea of consumerization. So I thought if we're going to have data democracy, then I would just kind of contrast it with data anarchy, even though I don't think data democracy means a damn thing. But you've got these situations, the IT supported BI, and then you've got the shadow IT where the business has gone around IT because IT was just too much of a problem. You've got secure access to data, you've got uncontrolled access to data, and that's a lot of the things that are happening at the moment with Hadoop is uncontrolled access to data. You've got managed self-service, which is people do like self-service, and like in the 1950s, self-service revolutionized retail. And ever since then, if anybody has ever managed to, it's a really neat trick if you're running a business, to put the customer in charge of doing a lot of the work to satisfy their own requirements. It's a really neat trick because you don't have to pay the customer. But it's also the customer much really approves of that kind of behavior. So managed self-service, but uncontrolled self-service is the anarchy counterpoint. Genuine defined capabilities, and the data anarchy is any capability. And this is, most of the stuff that's actually happening out here is happening as a result of I would call it schizophrenia in businesses, where some part of the operation of a business has decided it's going to do its own thing, and it's not the IT part, so they don't have the professionalism that IT, they're much faster, but they also get into trouble much faster. You've got data democracy is kind of about collaboration, but data anarchy is about independence. We've got standards, no standards, and we've got approved devices and bring your own device. And those are just two interesting counterpoints to actually think about if you're looking at the area of BI. Because once we've taken the analytics out of the game, we're then into every user, every person that works for an organisation should have whatever data is useful to them in order to be able to do their job better. So the question is, what should we give them? Well, part of it would be, in one way or another, it would have a lot of self-service, but it would also be managed in such a way that you would not have problems. So I'm just taking, the fact is, this is news, this is how consumers behave. There's two parts to news. One is news of what is actually happening, the other is why and how is it happening. And this is what I think is being delivered by BI now. It's like, it's a consumer thing. We want various, or depends on the news, but you want various analysis statistics, graphs, photos of what's going on so you properly understand what the news actually is. And that's data exploration. And I think that the thing that's happened in the past 5 years is that data exploration has come into BI, and it's not over yet by any manner of means, and it's a kind of an interesting thing. The difference between the old BI that we got, where you just get reports and things, and the new BI is you get to interact with the data, and people like interacting with things. They don't necessarily do it particularly well. They kind of have to be trained to do it if they're going to do it well. But this has just gradually ramped up in the past 10 years or so. You've got drill down and stuff like that, summary capabilities. You've got algorithmic capabilities. You've got exploratory via various different perspectives and topologically through the visual appearance of data. You've got, this is what I think of as the expansion beyond the spreadsheet, because the spreadsheet defined what you could do before. And this has started to be, an awful lot more can be done now and can be added into the equation. And you see that these are different actually technologies that deliver a lot of this. The options. For data, there's two possible approaches. The individuals can either understand reports, list groupings, or they understand visualizations, or they understand a combination of the two. And the thing that's happened with visualization that I find really, really interesting is that it's come into its own in the past 5 years, and it's also, in my opinion, it's really in its infancy because of this, is that there's no really good visualization technology that uses animation. But it's known that the brain responds best to change than to anything else. So if we wanted to actually communicate best a situation in terms of data, then it's probably best done with animation. But no one's got any theory as to how to do this right now. So it's an area that I think, maybe Yellowfin will do something in this area, but it's the companies in this space that are going to determine that. There are various animation work that has been done, but there's nothing that I've seen that where you look at an animation, you start making decisions from the animation, because that's the proof point. It's like I give you something, whether it's a report, whether it's columns of data, whether it's one visualization or another. I do something, I give you something, you look at it, and you can now start making decisions from it. That's what we're trying to enable. That's probably the only thing we're trying to enable. And this is, am I kind of reasonably on time? Oh, almost, only a few minutes over. This was the idea that there's an interaction going on between what BI is and what the person doing the job is. The idea that it's actually, BI should be an educative experience, should be a learning thing. And there's some, you can kind of look at this at your leisure, because I haven't got time to go through it, but it's extraordinary that if you actually want to remember, actually learn something, the best way is to actually do it, and do it and teach it is probably actually the absolutely best way. And the idea that we would have tools, not tools for people to use, but tools that actually educated the people as they used them, that would be a really, really neat thing. And I think that's actually going to happen in the BI space, And written loads of words, but I'm kind of run out of time. That graph didn't work, did it?
We'll give you a free copy of storyboard for you.
Yeah, I know. I've been hidebound by PowerPoint for years, you know? It's just... and so, I've come to the end, so thanks for your attention.